Okay, so here's our pulley problem. We're given two masses that are hanging off of each other. All the mass is in these hanging masses. There's no mass in the pulley, no mass in the string itself. The only purpose of the pulley really is to redirect the rope so it goes up and over and you can attach it to another mass. The given variables are M1 and M2. I usually like to mark given variables with a check mark. Again, if you found yourself still jamming in numbers right away on homework 4, you're going to find that at some point you have to not do that. So symbolic answers are going to become key. I'm asking you for the acceleration of each mass. Usually to keep track of those variables, I'm marking them with a question mark. And I already went through, I think, most of the problem last time because the steps 1 through 5 are extremely quick. The actual just solution ends up taking a little bit of time. So this particular problem ends up being very backloaded to step 6. I already identified my objects of interest. I identified the forces they each had on them. I decided on my axes. In fact, in this case, there's really only use for one axis. Everything's happening along a single axis. I already wrote down my force equations. I had, instead of an x and a y equation for a single object, like most problems that you've had on homework 4, we instead have a y equation for each of the two objects. They both have a tension acting up on them and the force of gravity or weight acting down on them. And whatever difference those two forces have to each other is what drives the acceleration of that mass. So, with that in mind, it's all alphabet soup at this point. Let's take stock of what we have, what we want, what's going on here. So this is really important when you're solving symbolically, is that you differentiate between variables you want, like the accelerations. In fact, those are the things we want, and the things that you're given and are allowed to put in the answer. M1 is given, M2 is given, so I'll check those off. And then included in that batch, of course, is G. G is always allowed. G is a stand-in for a particular number. But we find here that there's two variables which are in neither category, the tensions. So I'm going to add over here the don't know, don't care category. And in that category, we have T1 and T2. We usually mark these with a big cross out when we were doing kinematics problems, right? Those constant acceleration equations. So, of course, the reason why we had those variables in the constant acceleration equations is we always list out everything, but we found that we don't need all of them, right? We need a minimum of how many? 3 to get a fourth, don't know, don't care about a fifth. Now you might question, well, where did these variables come from now? I'm not just listing out all the possible variables that could be involved. The reason why T1 and T2 made their way in there is because I needed them to properly describe the system. Even if the problem doesn't mention them, the tension specifically, you know that a rope is attached to each one. So you're going to have to include a tension, right? So this is where the rules of the game for symbolic solutions come in. Remember, the rules of the game are you're allowed to express your answers in terms of given things. So if you want to introduce other variables that you think are necessary to describe the system, you should never hesitate to do that, because you can't just jump straight to the answer. You're going to have to systematically approach this, and if there are strings attached to your objects, you should include a tension. But you have to do some cleanup after yourself, okay? If you need scaffolding to paint someone's house, they don't mind if you use the scaffolding, but they want it removed when you are done. So we're going to have to make sure to get rid of the tensions by the end, because they're not allowed in the answer. You just made those variables up, so they cannot be in the answer. So we should mark those down. These are the don't know, don't care. And taking stock of the variables like this, there are those 3 general categories: things you want, things you know, and things you want to get out of there. As soon as you introduce them, which you need to describe the system, you have in mind that you need to clean up after yourself later. Here's the problem, though. right now we have two equations, right? This one and this one. But we have four unknowns. We have T1, T2, which we don't want, and A1 and A2, which we do want. You should probably know from math class that is not a solvable system, right? You cannot get four unknowns out of two equations. What's the most unknowns we could get out of this? Two, right? You can only get as many things as you have independent equations to get them, right? So there's obviously some impasse or roadblock that we need to punch through here, and this is a perfect opportunity to introduce your Pulley tricks, the quote-unquote things that will get you out of a jam and allow you to progress in a Pulley problem. So let me talk about those. Where do I put these? I'll try to sneak them in over here. These are your Pulley tricks. When you have a Pulley problem, you can use them. So here's the first trick. Let me pull out let me use a rope, okay? Here's a rope. It's always handy, okay? Now, if you have a string that is pinched off, so let's say I have this string here, and I'm going to pinch it from the middle, right? If I pinch it, it's very possible for one side of the string to be tight, like this side over here, right? And this side to be much looser, right? For a pinched off string, it's perfectly possible for there to be different tensions in different part of the string, okay? But if I don't pinch it off, then the tension kind of uniforms out, right? So you can't have that one part of the string is tighter than the other. It's either the whole thing is loose or the whole thing is tight, right? Does that make sense? Now, I should mention there's one exception, is if it's hanging vertically like this, of course it's not pinched off in any way, it still has different amounts of tension in it. The reason why is it tighter up at the top versus down at the bottom? Can anyone tell me? Yeah. It's exactly. So this part of the rope has to hold up the weight of everything below it, which includes not only this thingy on the bottom, but the entire rope below it, right? Whereas this rope down here has no such job, right? It doesn't have to hold up all the rope hanging off of it. If you've ever, say, hung a long rope, you'll notice it's way tighter at the top than at the bottom, okay? But remember, our ropes are massless too, so this is a real-world rope. Our magical physics ropes are massless. And so for that point, the point I'm trying to make here is that if we can assume that the rope is not pinched off and its mass is negligible, what we're guaranteed is that the tension is the same everywhere, okay? So that's my first trick. The tension in a freely running, and I guess freely running is the opposite of being pinched, right? So it's not being pinched. Okay, so the tension in a freely running massless rope is uniform. So that's my first trick. Now, how does that help me in my problem? Well, it helps me because this is a freely running massless rope. And the fact that the rope happens to run up and over this pulley, the only thing that the pulley does is redirects it, but the tightness in the rope is the tightness. So it helps me by realizing that the T1 and T2 are one and the same T. There is one tension in this rope, and that tension actually acts on both masses. So I can go over here to my situation and realize that my two unknowns here, T1 and T2, are really the same T. So while that unknown might appear several times, it is now the same unknown, and we are now two equations and only three unknowns, okay? Does that make sense? Now you might question, how is it possible, if this is really the same tension, how is it that that tension can have such different results where one of these masses, the smaller mass, is actually going to accelerate upward? What does that mean about the relative strengths of the tension and the gravity? Which one is stronger? Tension, right? So the net force in one can be upward because the tension exceeds its weight. But that exact same tension, what's the acceleration of the heavier one? Which way is it? Down, right? So the net force is which way? Down, which means which force is bigger? Gravity, right? So that same exact force is now smaller. Is it possible that the same tension could be bigger than one weight and smaller than the other? Sure, if the weights are different, right, the tension comes out to be somewhere between them, right? In fact, if we were going to rank these three forces, here's how do we rank them. So the tension in the string comes out to be somewhere between the two weights. The tension's enough to lift one while it is not enough to hold up the other. And that's in fact how the system ends up moving the way it is, with one mass accelerating upward and the other one accelerating downward. Are there any questions on that? Okay, so that my first trick got us down from 4 unknowns to 3 unknowns. The second trick is, and second and final trick, is going to reduce us down to a solvable 2 equations, 2 unknowns. Okay? So the second trick is this. These two objects cannot accelerate independently. They're attached, and they're attached by a rope, which we assume doesn't stretch and doesn't break. So they move together, right? If one mass goes up 5 meters, how much does the other one go down by? 5 meters, the same, right? If one has an upward velocity of 5 meters per second, the other one has a downward velocity of 5 meters per second, right? They're attached. Now, of course, displacement and velocity don't appear in my equation, but acceleration does. So if one is accelerating upwards a certain way, the other one's accelerating down at the same rate. If they weren't, then the rope between them would be getting shorter or longer, and that doesn't make sense. They're attached. So my second and final Pulley trick, which is very useful, is the objects that are attached must have coordinated motion. So you can't just assume they move and do whatever they want independently. And in my case, what I'm going to note is you have to be careful. The accelerations aren't the same. What's different about the accelerations? Direction, right? One is going up and the other one's going down. So they have the same size, but one is up and one is down. So if I wanted to write that, I would have to acknowledge that, where do I put it? I guess I'll put it down here. In this case, AY1, and I should label it, in this particular case, so this is not generally true. You'll have to figure out how to tweak this slightly for your homework. In this particular case, I would say the way that they are coordinated is that one acceleration is the negative of the other, right? Because one goes up and the other one goes down. Does that make sense? So now we should be all set. If you want, you can think of this as a third equation, right? So you now really have 3 equations. So 3 equations, you can get 3 unknowns. Although this third equation is so trivial, I prefer to think of it as if I'm solving for AY1, AY2 is negative AY1. So that's really just like 2 variables, right? Or it's now just the same variable. So I've reduced this down to 2 unknowns. So now I can safely attack the algebra with knowing that I'm going to get through to the end. So let me rewrite the equations. T minus m1g equals m1ay1. Notice that I left the subscript off the t because it doesn't need to be labeled t1 and t2 anymore. And then over here, t minus m2g equals m2. And then I'm going to plug in that the acceleration of the second mass is the negative of the first. So what I've basically just done is I've picked my horse, right? I've just picked that I'm going to solve for the acceleration 1. Acceleration 2 is just going to be the negative of whatever I get of that. So right now, here's what my plan is. I'm going to solve for this. It appears in two different places, but that's just an algebra problem. I have a bunch of known things, and I've got to get rid of t, right? T has got to get out of there, but at least it's a single t. So any suggestions for how I might get t out of there, clean up after myself? How do you usually get rid of a variable in two equations? Solve for t and plug it in the other. Then it's gone. Poof, it's gone. Okay? So let's solve them both for t. So from the first equation, t equals m1ay1 plus m1g. I'll solve for t in the other one. That's going to be, you see what I did there? I moved this over, became positive. Over here I'm going to move this over, that becomes positive. Yes? Is this algebra that you can get down with? Okay, so this is m2g, and then I'm going to factor this minus sign out because I don't like it in there. It makes me have to write a bunch of parentheses I don't need to. So there I have it. I have two different expressions for t, right? And if I leave off the very left-hand side, I suddenly have two sides to work with, not involving a t, right? So I'm just going to keep this. Now I know that this, again, really might tax some people's ability to do algebra. I don't know what to say about that since it's a prereq. So I'll just kind of go through it, not super slowly. So I want to isolate ay1. It appears in two different places at the moment. How do I isolate a variable in algebra? How do I get it in one place? That's right. So get all those terms to one side and factor out the variable I want. So I get the acceleration times crap, right? Divide by crap, and that's how I'm going to do it, right? So I'll move this term over here to join its friends. I'll get this one over here, get out of there so I can factor everything out of the left-hand side. Looks like I'm going to have to clear a little space. So I'm going to get m1ay1 plus m2ay2 over here. Oops, no, it's y1. I chose to solve for the acceleration of 1, so that's going to have to, all the terms have that. And then let's throw in some friends over here, m2g minus m1g. When you throw it on the other side, it switches sign. Okay, so here's our factoring business. Factor out that. For some reason, g wants to get into the act. G is a constant, so it doesn't matter, but it likes factoring too, I guess. And we're pretty much done. So we have our a acceleration times some stuff. We divide by that. ay1 is equal to m2 minus m1 over m2 plus m1. I made a few little shuffles around for aesthetic purposes, which hopefully don't disturb you. I put the g all the way out on the side. I made the 2's and the 1's line up in the numerator denominator. It doesn't matter. Okay. And remember that ay2, we do also want that, but that's easy now, right? It's just the negative of this, right? Oops. So those are my answers. And they are in terms of the masses and g. So as advertised, you can get the answers in terms of m, the masses, and known constants. These are technically y components, of course, so they are bound to a particular y-axis. But I'm going to leave it there just because they're more interesting to discuss that way. Are there any questions about the algebra I used to get those before I go and discuss these results? Okay, so simple ideas, and it just happened to be that the algebra was a little tangled up in terms of solving for the things that I wanted to. Okay, so the thing that makes this hard is just algebra. Okay, the physics was easy to set up. We started from simple principles that each mass has a tension and a force of gravity acting on it. And then we simply said that the tension is the same tension because it's the same rope. And we acknowledged that the accelerations would have to be equal and opposite. And from that, we solved and we got this. These are the accelerations of each mass. Now, there was definitely quite a bit of algebra involved in the problem, and so it's very likely that we could have made a mistake somewhere, right? We could have accidentally lost the minus sign or something, and so this is where the beauty of checking your limits comes in. I showed you this with the inclined plane. It's a way of error checking symbolic solutions, so I'm going to try it out here, and we'll find out what's happening. Let's try it out. So these Pulley tricks, use them on your homework. Use them and adapt them. Okay? You shouldn't just be looking to apply these equations on the homework. This is not a derivation. This is the answer to this problem. I'll give you another problem with a different answer. You have to go through this process yourself. So let's check limits. So we're trying to be clever and think of cases where we kind of know what should happen. I left the diagram up on purpose so you can kind of visually imagine this. Can anyone suggest a limit where we know what should happen? You probably don't have a lot of intuition if this is 3.7 times this, but what would be a case where you know what should happen? Yeah. If the masses are the same, what should the acceleration be if the masses are exactly the same? 0. Let's check it. So our first limit is that the masses are equal. Are these going to give 0? Yeah, look, the difference in the masses is in the numerator, right? So if the masses are the same, that makes it 0. This is where you find out real quick if you accidentally have the sum of the masses up top and the difference in the masses down below, because then you have problems, right? You have a 0 in the denominator. So the acceleration would be infinity? No. Okay? So that seems to check out. So we expect that the acceleration should both be 0 and the equations yield that they are. So that's my first limit. My symbolic solutions have passed that test. Anyone think of another case where you know what should happen? Yeah. If one mass is 0, so let's make the m1 equal to 0, then what should be the acceleration of the other mass? What's it going to do? Free fall. So if my plus y-axis is upward, what should the acceleration be? Minus g, right? Remember, the negative is not inside the g, so the minus would be out front. So that's just our expectation, right? If one of the masses basically is gone, we basically cut it off. We cut off m1, m2 should free fall. Let's check it out. Let's make sure that happens. So I take my expression for ay2 with a negative in the front, and I put in that the mass 1 is 0. What's that quantity in parentheses now? It's 1. So what do we get? Minus g. Check. Okay. It works out. What would be another pretty similar limit? Other than the mass 1 being 0. Mass 2 being 0? Okay. Let's try that. So if we cut off at mass 1, mass 2. Mass 2 is gone now. What should be the acceleration of mass 1? Should be free fall, right? Plus g or minus g? It's going to fall up or down? If you cut this mass off, this is going to fly into the sky? Really? If you cut this mass off, this one should fall down, right? Should be minus g, right? If you cut off either mass, the other one falls down, right, in free fall. Okay? So we're going to have some problems if our expressions do not yield this. So let's plug in ay1. ay1, and we'll plug in that mass 2 is 0. What's the quantity in parentheses now? Still negative 1, or sorry, negative 1, which still makes this minus g, right? Checks out. If there's a mistake in our symbolic answers, it's hiding out really well, okay? And of course, at this point, we might conclude tentatively that there is no such mistake, okay? We've checked our limits and noticed that everything seems to gel with physical intuition. That's the beauty of when you get an answer in physics class, you don't necessarily have that head check in math class. And we also get a further picture of the answer. These accelerations range anywhere from 0, when the masses are equal, to free fall when one mass is much, much, much bigger than the other. And generally speaking, these range from 0 up to free fall, and they are generically could be anywhere in between that, right? Never, the acceleration can't be any less than 0, and there's no way to make it fall faster than free fall either. The answers are somewhere in between. If you look at how they're phrased, you can tell this number, generally speaking, is some fraction, which is between 0 and 1. And of course, then it's multiplied by g. Look at it. It's the difference in the masses in the top and the sum of them in the denominator, right? So that means that the numerator is always smaller than the denominator, right? And if the numerator is smaller than the denominator, that's always a number that's going to be less than 1, right? Does that make sense? Okay, so checking limits helps you understand the character of the answer often, okay? Are there any questions on this Pulley problem before I change gears and talk about friction? Okay, so you have some of this stuff in your homework that you have coming up, homework 5. And I guess the other thing that I should mention students often have trouble with, like your lab has a question, or your lab setup looks like this. So it's a pulley on an incline. Now, as much as that might seem challenging, basically these pulley problems, it's like two for one, okay? It's like you can work this problem if you want to use your inclined plane axes, something like that. You generally want to set one axis parallel to the incline and one perpendicular. The x can be uphill or downhill, it doesn't matter. And you set up all your stuff as if that was just an inclined plane problem. You'd of course include a tension, but you're basically working it as that problem alone. Maybe for this one, you might set the axis like that. So you're basically setting up two problems, and then how do you get them to talk to each other? Well, the tensions are equal, and the accelerations are related. So then that allows you to ram your two problems together into one mega problem and just solve for something, right? So that's basically how you do that. You can even use different axes, right? It's okay, because the connective tissue is going to be that the tensions are the same size and the accelerations have some relative relationship. For instance, in this case, this looks like it's going to have an acceleration. Let's say the accelerations are like this, right? So this one has an acceleration in the positive x direction, and this one has an acceleration in the negative y direction, right? So your equation is just going to be this. One of them accelerates with the opposite sign as the other, right? And that's just simply because of the way you chose your axes. So you can, even though one is accelerating along an x direction and one of them accelerating along a y direction, you can still ram the two problems together, right? Because if this acceleration is plus 5 meters per second squared, this one will be minus 5 meters per second squared, right? They're attached. They're attached by a rope. Okay, so those are some ideas of how to attack pulley problems. Let's talk about friction. Now, first of all, I should preface, friction is hard. Friction is complicated. It's something that you can do a graduate degree on. Friction is extremely has a lot of stuff going on. And we would not ever even attempt to include it at this stage of a course when you're first getting accustomed to physics if it weren't so important to our everyday lives that we need to get it in there somehow, right? To say that all things are frictionless would be just not really representative of the world we live in. So what we do is we just kind of patch together something that will work well enough, okay? It's going to be one of the first times in this class we use what's called an empirical formula. An empirical formula is something that we kind of just patch together from experiment, okay? So something that we experimentally find works pretty well, and we just kind of go with it, okay? So I just wanted to give you that initial heads up that friction is, we're going to take a little bit of a different approach, okay? So the force of friction. One of the very first things that we need to acknowledge is that there are actually kind of two different types of friction. Okay? So one kind of friction is, of course, you're trying to drag something along off the floor or something like that, and you feel that there's this force that's holding you back, right? That's called kinetic friction. That's when the object is sliding across the surface like that, and there's something that opposes your motion. There's also the kind of friction that prevents you from starting something in the first place, right? So if I'm trying to get something heavy moving, I might not be able to budge it at all, right? Well, the kind of friction which keeps you from moving something is called static friction, static for not moving. And so one of the things we immediately make as a concession to this kind of patchwork way we deal with friction is we take the same phenomenon, friction, and we split it up into two prongs, static friction and kinetic friction. So force of static friction so this is the kind of force that acts when an object is at rest with respect to the surface it's on. By the way, if you don't know that abbreviation, WRT, it means with respect to, okay? So for that particular phenomenon in which friction acts, when it's, we need to talk about the size and direction. We need to come up with rules of thumb for how this might act. Then the force of kinetic friction. That is when an object is sliding across a surface. So when an object moves with respect to the surface it's on. And by the way, and so we're going to have to talk about what are the rules of thumb for size and direction of that type of friction. Now, you notice that I didn't just say when an object is at rest and when an object moves. It's all about relative to the surface it's on, right? So to give you an example, right, have you ever had the experience you maybe put a coffee cup on top of your car and you start driving away, realizing you forgot it there? No one? No one besides me? Okay. So if you're lucky enough, you can stop and it's still there, right? What kind of friction do you have to thank for not having to go buy a new cup of coffee? It's actually static friction, because while both the roof of your car and the coffee cup were in motion, they were at rest with respect to each other, right? So that's the kind of friction where the two aren't actively sliding against each other. If the coffee cup is actually in the act of sliding against your roof, then we would call that kinetic friction. Okay, so let's talk about first the direction. The direction part's easy, okay? So force of static friction opposes the quote-unquote potential motion. So you're, of course, not sliding against the surface yet, but it's keeping you from doing so. And so it is, by the way, and if this is not already obvious, it's parallel to the surface. Okay, so it's parallel to the surface because, of course, no motion would be possible perpendicular to the surface. The normal force forbids it. Unless you want to lift the object up, and of course then you don't have any friction at all because it's not touching the surface anymore. Okay, so the inherently implied thing is that friction is parallel to the surface. On the kinetic friction side, it just simply opposes the actual motion. And again, it's going to be parallel to the surface. So there's nothing in the direction that would seem to imply that there's a huge bit of difference. Friction is always trying to oppose what's either going to happen or what is happening. The reason why we do split this off into a two-pronged attack is because the sizes are very different. We need a very different approach for size. Okay. Before I do that, I guess I should talk about notation. So for me, I'm going to indicate force of friction as F sub F. So the big F is for force, of course, and then the small f is for friction. Now, that gets a little bit awkward when I need to then further subdivide the force into static and kinetic parts. So I'll use force of friction comma static for static friction, force of kinetic friction, force of friction comma kinetic. And of course, if I want to refer to the size of just the size of any force, I leave off the vector hat. So that's what I like to use, and that's something that all of my solutions will be keyed to this. So just be aware of that. There's another common notation, probably more common than this. I don't know where I got this weird idiosyncratic thing, but I've been using it a long time. Sometimes for friction, just to save a letter, they'll write friction like this. So instead of a capital F, it's like a lowercase cursive f. And that means not just any force, but the force of friction specifically. So that basically just lets you have just a single subscript, is it static or kinetic? Okay? So if you ever see that, you know what that means. Okay? I can't remember what the nominally official textbook uses, but those are different ways you'll see this force. So the big thing is to talk about size. So what I'm going to do first is I'm just going to give you, just to complete this chart, I'm going to give you the answers, and then I'll go back and discuss them. Okay? The size of the static frictional force is given by this. It's actually a range. And the size of the kinetic friction force is not a range. So you can start to see big differences there. And that's why we need to talk about friction in these two different pieces. The force of static friction varies anywhere from 0 up to a maximum value, and don't worry about what that stuff is right there. And then, in contrast, the kinetic frictional force is a constant. So that completes the chart. And the only thing I need to do remaining is to explain to you what's going on with these sizes. How do you compute the size? And, of course, doing some example problems. So I don't want to leave you completely hanging out there on your own with just this. So once I introduce the theory, I'm going to show you some examples. Now, I'm going to start with kinetic friction because it's easier. It's just a constant. So let's talk about that first. So kinetic friction force, how is its size determined? So this is where we get into the empirical stuff, the stuff that we talked about that just experimentally comes from experiment. So if you go into a lab, and you will go into a lab later this week, you will discover something. You will discover that how much friction is going to be present has to do with how hard an object is pushed into a surface, right? So for instance, if I get a sense of how much friction I encounter pushing this table back and forth, and then I add additional force which is going to push the table harder into contact with the surface, right? You can imagine if I push the table harder into contact with the surface, it's harder to push around, right? Does that make sense? I mean, you can try it yourself, right? This is easy. Push your hands together harder into harder contact, and friction is harder, right? So what we find is that experimentally, we find that the force of friction is directly proportional to the contact force between the object and surface. So if we find that if we push two surfaces twice as hard together, we'll have twice as much friction. Now, the how hard two things are pushed together, we need a kind of a meaningful way to quantify that, and we have a perfect quantity to do that. So let's say we have an object on a surface. One of the forces, certainly that very commonly causes them to have contact, is gravity, right? Gravity tries to pull the object through the surface, and in the process creates contact. So a common misconception is that gravity is the contact force. Always, it is in this situation, but if you're doing it sideways, right, it's not gravity that's driving the contact, right? So it could be other things. Even in this scenario, right, like I had with this table, right, if I put an additional pushing force, now I have not one but two forces that are creating contact, right? Well, we have a force called the normal force whose whole job is to cancel off those forces, and so it's the perfect aggregator of any and all contact, okay? So the normal force has to cancel off all of these things that are causing the contact, and so it's a perfect measure of how much contact there is, right? So the contact force is basically measured by the normal force. So we find that the force of friction is directly proportional to the normal force. Okay? So, there's a second thing though. It's not just about contact force. Because you probably know that if you push, say, two pieces of concrete with a certain amount of contact force between them, you're not going to get the same amount of friction when you slide them as if you push two pieces of ice together, right? Ice is slippery, right? We call it, that it somehow has a different property, right? So the completion of this formula is this thing right here. This is mu sub k. It is another usage of the Greek letter mu. We used it for the first time as a prefix, meaning micro, 10 to the minus 6th. This has nothing to do with that. It's just a usage of that same Greek letter. Here's what that is. So mu sub k is called the coefficient of kinetic friction. It is basically a rating for the roughness of the surfaces involved. So it rates the roughness of the surfaces.